Okay, hello and welcome to our Ingram Micro and Corning webinar session for today. My name is Igor Zainko and I'm the marketing manager at Corning, responsible for channel distribution, and I'm happy that you're all attending today. Today we want to introduce you to Corning's data center solutions and guide you through the requirements and our products. Please be informed that we are recording this session and Ingram Micro will share this via the website on Ingram Micro Middle East, and it will be posted as well on other social medias. For now, please be informed that you are on mute to ensure a better audio quality. If you have a question, we'd like to ask you to post it in the chat window on the bottom right, or ask us at the end of the session of the presentation. Now I'd like you to introduce today's presenter, Mahmoud Al-Ghazali. He's Key Account Manager for Middle East region and our regional data center sales expert. Mahmoud, the stage is yours.
Thanks, Igor. I would like to welcome everyone to the presentation. And I first want to introduce myself. So my name is Mahmoud. I'm Corning Data Center Sales Manager for the Middle East region. Today I've been start the presentation with the Transceiver Technologies, which is actually very important for our data center solutions. And once we get to understand the transceivers which we have inside the data centers, we will be able to understand the fiber optic connectivity inside the data centers. So basically, we do have a lot of transceivers in the market, 10 gigabit, 40 gigabit, 100 gigabit, all the way up to 400 gigabit. And this graph shows you the development or the number of units sold from 2016 until today, and as well the expected growth of these transceivers inside data centers until 2024. As you can see here that 40 gigabit transceivers were famous in the last 4 years, and now we started to see more 100 gigabit transceivers in our data centers, especially the connectivity between the switches, the edge switch and the distribution switch or the spinal leaf. And also there's some development we started seeing actually the 400 gigabit transceivers in 2020 and 2019. And we're expecting more growth into this speed or connectivity inside our data centers. So we did a survey, it was like around 3-4 years ago, with the active manufacturers in the switching industry, Cisco, Juniper, Arista, also in the storage like Brocade, and also the transceiver vendors themselves, companies like Venisar, FIT, Mellonix, Avago. And based on this, we came to learn the following. Currently, for the 10 gigabit uplinks, we use the SFP transceivers. The SFP transceiver, as you can see in the picture, it uses 2 fibers. One fiber is transmitting 10 gigabit, and the second fiber is receiving the 10 gigabit. Okay. This is how the transceiver looks like. It uses the LC connectivity or the LC connectors, and everything is running on 2 fibers. When we go to higher speeds, we start using different types of transceivers, like the one we see in the picture now. It's called the MPO QSFP transceiver. This one uses 8 fibers. 4 fibers are transmitting 10 gigabit, for example, in the 40 gigabit transceivers, and 4 fibers are receiving 10 gigabits. So in total, 40 gigabit is transmitted on 4 fibers, and 40 gigabit is received on 4 fibers. They are using the MPO or the MTP connector, which has 12 fibers. But please note that the 4 fibers in the middle is not used. It's not used at all. So it's blank, it's like blind. Another type of transceivers, we have the QSFP WDM. In the example we're seeing, it's a type of a WDM called the bidirectional WDM transceivers. Now in this transceiver, It uses two wavelengths, and that's why it's called wavelength division multiplexer. The first wavelength is 850 nanometer, and the second one is 910 nanometer. And then it transmits and receives on the same fiber. That's why it's called bidirectional, because the signal is going back and forth on the same fiber. Each wavelength is carrying 20 gigabit of signal. So on the first fiber, we've got 20 gigabit transmitted and received. And on the second fiber, we've got 20 gigabit transmitted and received. And this is a 40 gigabit BiDi transceiver. Or if it's a 100 gigabit BiDi transceiver, it's going to be 50 gigabit transmit on one fiber and receive, and another 50 gigabit transmit on the second fiber and receive. Also, there's different type of transceivers which also use multiple wavelengths. This actually can go, this transceiver is called the WDM or the SWDM or the CWDM, and they can go for longer distances than the BiDi. They work different than the BiDi. They transmit 4 different wavelengths, which is 850, 880, 910, and 940 nanometers. And each wavelength is carrying 10 gigabit of signal. So transmit 4 wavelengths of 10 gigabit, which is 40 gigabit, and then receive on the second fiber the 40 gigabit on, over 4 different wavelengths. As you can see, it works a bit different than the BiDi. So SWDM and BiDi, they are not compatible to each another. Although both of them, they work on 2 fibers, but they are not compatible to each another. This is a closer look on the QSFP transceiver, MPO. And you could see it's an MPO or an MTP kind of like footprint. It has 4 fibers transmitting 10G and 4 fibers receiving 10G. And we use the MPO connector, which has 12 fibers, but we are actually using 8 fibers of them. The first 4 fibers transmitting 10 gigabit, and the last 4 fibers receiving the 10 gigabit. The 4 fibers in the middle are empty or not used. In summary, this is some of the famous transceivers now we have in our data centers. And you can see on the x-axis, we've got the 10 gigabit all the way to the 400 gigabit. Then on the y-axis, the different types of transceivers, whether it's multi-mode or single mode. And is it a 2-fiber transceiver or a duplex transceiver or a parallel 8-fiber transceiver, multi-mode or single mode. So we use the SR, for example, like to simplify here in the table, we've got the short reach 10 gigabit transceiver. This can go up to 400 meters on OM4 fibers. Okay. And then if you want to go for 40 gigabit, we have the BiDi, which goes up to 150 meters, or the SWDM4, which can go up to 350 meters of 40 gigabit transmission. Then we have here the 100 gigabit BiDi, which can go up to 100 meters, and the SWDM4, which also can go up to 100 meters. Now, also one more thing important in this table, that everything in light blue is actually an industry multi-source agreement. Okay, so it's not a standard, it's not an IEEE standard. Only things are which highlighted on in black bold is actually an IEEE standard, and also blue font is also an IEEE standard. Sorry, the black ones is pending, and it's just a draft, and the blue is actually released or published by the IEEE standard. Now, this is, for example, the duplex multi-mode transceivers on 10G, 40G, and 100G, and they are not available in higher speeds than the 100 gigabit systems. Now, if we go to parallel, we have the SR4, which is the MPO QSFP, which goes to up to 150 meters. And there's an extended SR4, which can go up to 400 meters. So again, here's a very important thing which we need to always know, that inside our data centers, the first thing we need to always know, what is the customer looking for, which speed. Is he looking for 10 gigabit connectivity, 40 gigabit connectivity, 100 gigabit connectivity? And then the second question which always comes, is what is the length, for how long, like what is the maximum length I have in my data center. And based on that, I can choose which type of transceiver and as well, sorry, which type of fiber. When we go to single mode, and single mode, we use it for longer distance connectivity. For example, a 40 gigabit LR4, which works in 2 fibers, can go up to 10 kilometers. The LR4L can go up to 2 kilometers. And also note that the longer the distance, the more expensive the transceiver is. So for example, if I'm designing a data center and the distance, let's say, for example, is 600 meters. 600 meters, I would not design an active transceivers using the LR4 because it's going to be very expensive compared to the LR4L, which is only 2 kilometers. So I will try to utilize the shortest or the least possible transceiver, which covers the least or the less distance. So these are mainly the most famous types. But of course, if you go to like Cisco website, HPE, Dell, you will see more options, but most of them are either on 2 fiber system or on 8 fiber systems. And the 100G, what is very famous now is the BiDi 100G, which we see a lot in the data centers. You also see the ESR4 and the SR4 in our data centers. And we started seeing the single mode DR, which is 500 meters, because some of the big data centers like the service providers or the hyperscale data centers, the distances can reach up to 500 meters. And of course, in connectivity with different data center buildings, like in a data center campus, you will see the FR, the fiber reach, which goes to 2 kilometers, and the LR, which goes to 10 kilometers. Now, for the 200G and the 400G, I will speak in more details to try and explain how do they work in the coming slides. So this is the 200G. It has 4 transmitters, which is transmitting 50 gig, which is 50 times 4 is 200. Then it has 4 receivers, which is the receiving 50 gig, which is 200. So it has also 8 fibers. Now, in the WDM multimode, which is a 2 fiber systems LC, it doesn't work. It failed, actually. They tried to do it, but it couldn't. The WDM transceivers were not approved by the IEEE standard. But for single mode, we have the LR4, which can go up to 10 kilometers, and then the FR4, which can go up to 2 kilometers. And this can be connected on 2 fibers using the LC connectors. As of for multi-mode, if you still want to do multi-mode, we have the 200G SR, which works on 8 fibers. Each fiber is transmitting 50 gigabit. 4 fibers transmitting 50 gigabit and 4 fibers receiving 50 gigabit. And then also for 500 and 600 meters, we have the DR4 on single mode, which is it's very important to know that the price of the transceivers is always very important for us. So DR4 is cheaper than the FR4, which is cheaper from the LR4. So yes, this WDM single mode transceivers, they use 2 fibers, and this one, the DR4 uses 8 fibers. But the price of the transceivers is very important for us to know to choose the right transceiver. For the 400 gig, because the maximum transceiver speed we have now, or transmitter or receiver speed we have now is 50 gigabit. So we have to use 8 fibers to transmit 50 gigabit, which is 400 gigabit, and then 8 fibers to receive the 50 gigabit, which is 400 gigabit. Again, there is no WDM multi-mode solution for the 400 gigabit. On the single mode, we have the 2 fiber system, or the WDM single mode system, working on LC connectivity. LR8, 10 kilometers, FR8, 2 kilometers. And then in the parallel, we have the 2 wavelengths. So this one is actually a mix between the WDM and the parallel. So here they're using 8 fibers, but on each fiber, there is a BiDi 100 gigabit transceiver, which is transmitting and receiving 50 gigabits. That's why it has two different wavelengths, and they use the 8 fibers to transmit and receive the 50 gigabit, which is in total 400 G. They call that the SR4.2. Another type available in the market is the WDM, it's the SR8. And in the SR8, it uses 16 fibers. Each fiber is transmitting 50 gigabit. So 8 fibers transmit 50 gigabit and 8 fibers receive 50 gigabit. But the problem in this transceiver that most of the cabling vendors did not develop an MTP of 16 fibers. So the MTP is available, or the MPO is available now in the market, is the 8 fiber version, the 12 fiber version, and the 24 fiber version. But the 16 is not yet released by any brand. We don't see it much. And most of the customers who went for 400G transceivers ended up going for the SR4.2 or the DR4, because the DR4 as well works on 8 fibers and they can go up to 500 and 600 meters. Now, one more important thing in data center designs, the concept of breakouts. So this means that you can actually break out the 40 gigabit transceiver, into 410G. So here's an example for a line card which has 48 ports of 10G. In total, this is equal to 480 gigabit transmission power. This is in comparison with one line card of 36 MTPs or QSFPs, and each QSFP is 40 gigabits. So 36 times 40 is equal to 144 10 gigabits, which is 1,440 gigabits. So theoretically, if I can break these transceivers using these breakout cables, each QSFP transceiver will be connecting to 4 of these SFPs. So every time we are consolidating or aggregating the 10 gigabit ports to 140 gigabit ports, we can save a lot of cost to our customers. So here, one line card of 36 QSFPs and 36 QSFPs can replace 3 line cards of the 48 SFPs with 144 SFPs. And this saves a lot in the electronics. And a lot of customers have been doing this now, aggregating the 10 gigabit ports from one side to a 40 gigabit ports. So this is in like calculation. A line card of 48 SFPs or 480 gigabit costs around 45,000 euros. 48 SFPs will cost around 43.2 thousand euros. In total, the cost per port is around 1,837 euros. Now, when I do the aggregation, the line card, yes, is more expensive, is 70,000 euros versus 45,000 euros of the 10 gigabit line cards. The QSFP as well, they are more expensive. They are 64,000 euros compared to 43,000 euros. But when I divide by 144 10 gigabit ports, I end up with more than or almost 50% saving in my electronics. And when I save 50% of the electronics, I can also save more than 50% of power, because now I have less electronics in my data center. So it immediately impact the power, and as well, it impact as well the cost of cooling. So the cost not only of the capital investment, which is like the price of the transceivers goes down, but also the operation cost of the data center itself is affected because of this reduction. And we can do breaks for 40 gigabit to 410Gs, the 100 gigabit to 425, the 200 into 450. So breakouts can happen as well as we go. So for the 400 gigabit, I already discussed this. What we have now in the market is the MPO 12 and the MPO 24. You can see this, these two. This is the MPO, which has 16. I'm honest, I didn't see it from any of the vendors. No one is promoting this one. However, we as Corning, we are working on different types of connectivity other than the MPOs and the LCs. And this connectivity, we have a joint kind of like a development with a company called Synco. And this is a Synco Corning connector, or a Corning Synco connector. And you can see its size compared to the LC duplex connector. Also, there is another connector we're working on. It's called the MDC, or the mini duplex connector. This one also Corning is developing with US Connect. And the idea of this connector that you will have like 8 mini duplex connectors bundled, as you can see, so that you can connect to the transceiver and you can do your breakouts easily physically from the connector itself, because they're physically kind of like separated. And in this case, the 400G DR4 can be easily broke into 400G DRs, or the transceivers. So this is, in summary, the transceivers which we have in our data centers, which actually we need to take care of while, or consider while we are designing our data centers. Now I will go to the cabling solution which supports these transceivers. So before the parallel transceivers, which is the 8-fiber transceivers, Corning 12 years ago came up with the Edge solution. And the Edge solution was based on voice of a customer, where we sat with our customers, like all customers around the region globally, and we spoke about what concerns the customers have. So the main points the customer had back then in 2009, it was the airflow. We wanted to improve the airflow. They need to be able to manage the slack, the extra lengths of cables. They wanted to increase the density of fiber, as you can see, because of the transceivers and because most of the servers and electronics now inside the data centers are connected with fiber and not in copper. It needs to be very easy and fast to be installed and allow moves, adds, and changes, and also future-proof and scalable for high-speed connectivity. Also, they came up with points like we need smaller cables, higher density, we need to be able to do tighter bends, and so on. So these like most of the points they were discussing back then. So Corning developed a new fiber back then. I think it was 2008, 2009, and it was the Corning clear curve multi-mode, which is used commonly. The multi-mode is used in data centers more than the single mode. And it was almost 90% better in bending radius than the standard multi-mode fiber. And based on this fiber, we were able to do smaller hardware, increase the density, and be able to address all the customers' concerns. So the solution now is more density. Okay, we doubled the density, I remember, 100%. Faster in deployment. The polarity was easy to manage, and I'll show it to you later how we manage polarity in our solutions. And it was scalable back then in 2010 and 2011 and 12. It was only considered up to 100 gigabit transceivers because we didn't have back then the 200G and the 400G. And as well, it was cost effective. So these are the components of the Edge solution, basically the patch panels, the trunks, and the modules and cassettes. And as you can see, we have a lot of options, like the floor mounting option. You can do actually panels under the raised floor if there is clearance there. You can also mount the panels on the ladders or the cable trays, which is above the cabinets. It doesn't have to be also inside the cabinets. Even the solution allowed field splicing, so you can mix between pre-terminated solution and splicing solution, and a lot of other features. So the trunks were reduced in diameter, and I think until today it's the smallest diameter size, like diameter trunks. Also, we increased the fiber density inside the trunks. We can supply fiber optic trunks up to 864 fiber inside a trunk. All of them are bend insensitive, 90% better in bending than standard multi-mode fiber. And the cable diameter was reduced by around 32%. Also, we made it easy. We added the pulling grips so that you can easily pull it inside your cable path, and as well added the forcation kits, which we use to strain relief the cables inside the panels. We gave panels with a lot of strain relief slots so that you can manage multiple cables easily. For the module size was reduced. It has 12 fibers. We added the shutters. This is like the dust shutters instead of the dust caps. And it's you can actually see, you can test it as well. You can see like red light through it. Also, the loss was reduced back then. So these modules were like low loss. It gave like low loss compared to the standard loss. And also you have them in LC connectivity, and also you have them in MTP connectivity or MPO connectivity as well, which allows you to connect to any type of transceiver. Hardware or the patch panels, we had three options: the 144 fiber patch panel in 1U, the 288 fiber patch panel in 2U, and the 576 fiber patch panel in 4U. As you can see, it can easily manage multiple cables from the backside and directly connect to the modules, and all the modules are physically separated from each another, so to allow you easily access the modules without interrupting any other connectivity. So solution was 50% better in the bending radius. It was faster by 35%. Also, we had simple inventory because we have the universal polarity. I'll show you the universal polarity. I have it in the coming slides now to explain it more. And it easily will allow you to migrate to 40 gigabit or 100 gigabit, and it saved around 17% of your time. So all fiber which is used in Corning data centers are bend insensitive, whether it's a multi-mode fiber or a single mode fiber. For the single mode fiber, we use the ultra bend single mode fibers, which complies to 657A1. And we are the only vendor who actually do that. For data centers, use the 657 standard, which is commonly used in the FTTH and the GPON applications. But Corning as well use it because of the tighter bends and the high density of fiber inside the data centers. We are the only vendor as well who have the multi-mode bend insensitive version as well, which you can bend your fiber up to 7.5 millimeter bending radius without any loss. Polarity. So basically the transceivers, the transmitter from one side needs to connect to the receiver from the other side. Meanwhile, the transmitter on the second side needs to connect to the receiver of the first side. In order to, and of course in data centers, we have multiple of connectivity and cross connectivity. So it's very hard to maintain this polarity, specifically when you have a lot of cross connections inside your data centers. So your solution needs to be polarity managed in an easier way. So how do we do it? Basically, I'll skip all of that over here. This is how our modules or cassettes look like from the inside. So this is the trunk, which has 12 fibers, blue, orange, green, all the way till aqua. Okay. And then this is the module. And this is how the module is actually cabled. So if you see here, the trunk has the fibers in the right order, which is blue, orange, green, brown, slate, white, red, black, yellow, violet, pink, aqua. Then in the module, it's not the same. In the module, you have the blue, which is the first fiber, and the aqua, which is the last fiber. This forms the first port. Then the orange, the second fiber, and then the pink, which is the second last fiber, and forms the second port, and so on. So the first was the last and the first port, all the way when you reach to the two in the middle, which forms the last port. I want you to have a look or look at the red arrow, and it's on the blue fiber. It goes to the trunk, then it comes back automatically on the aqua fiber. Okay, because of this universal polarity system in Corning. If you look at the blue arrow, it's on the blue fiber, goes automatically and come back on the aqua fiber or the receiver from the other side. So this is actually a Corning patent feature, which is called the universal polarity system. Both modules and cassettes are exactly the same. The wire are exactly the same. Of course, the trunk is the same, and polarity is easily controlled in the Corning solution. Now, if you go to other vendors, you will notice that you need to switch or flip the patch cord for it to work. So one patch cord would be straight from one side, and the other side it would be flipped. Or they would sell you two types of cassettes. They call it the straight cassette and the flip cassette. Or they sell you one cassette, but you have to connect it straight from one side and flip it from the other side. So in Corning, we don't have all of these issues, and it's much easier for us to control the polarity. Only one thing you need to note here, that we do have a flip in our system as well, but the flip is in the trunk. So the trunk on this side is blue to aqua, but when you go to the other side, it's actually aqua to blue. So Corning flip is not in the modules and it's not in the patch cords like all other vendors. Corning flip is actually in the trunk itself, because we only have one trunk in our system, but two modules and two patch cords. And that's why we chose to do our flip in the trunk and not in the modules or the cassettes. So in summary, this is today's 10 gigabit connectivity, which is module, trunk, and then a module, basic. And then you can migrate by removing these modules or cassettes and then adding the MTP to MTP adapters, and then the MTP to MTP jumpers, and connect to your high-speed 40 gigabit or 100 gigabit, which we know now it works on 8 fibers. Only one thing you need to note here, we took the 12 fibers, which was giving you 6 ports or links LC duplex, and you migrated into one port of 40G, which is using 8 fibers. So the 4 fibers in the middle are actually lost. And this is like the disadvantage of migrating on a 12 fiber system into an 8 fiber transceiver, is that you have to lose the 4 fibers in the middle. So basically, to solve this problem back then, I think it was 2014 when we came up with the Edge AO, or Advanced Optics, we started using conversion modules, which will take 2 MPOs of 12, which is in total 24 fibers, and it will break them into 3 MPOs of 8. So we take the 4 fibers from the first MTP or MPO, the 4 fibers which is unused in the other or the second MTP, and then we form one additional port of 8 fibers. And by that we convert from a 2 times 12 system into a 3 times 8 system. Also, we have it into a 4 times 12 system. We can convert it into 6 times 8 system. By that, we get you back the 4 fibers, which is lost because of the migration. But one disadvantage which we had back then in this system is that we doubled the MTP connectivity. So we theoretically increase the loss by almost 50%. You can do it with modules. You can also do it with patch cords. So you can connect directly to the trunks, 2 12s, and convert them into 3 8s. Okay. So one more advantage we have in Corning is the clean advantage. So everything we produce in our factory, we tested to make sure that it's a low loss connectivity, whether it's an LC or an MTP, and then we pack it and we ship it to you 100% cleaned and tested. So you don't have to do the cleaning on site. So once you get it, you just remove the pack and connect directly and do your test. So this saves you around 17% during the installation time. And of course, it saves you the consumables, because you need tissues and alcohol, isopropyl alcohol, a lot of things which you use for cleaning. So that saves almost 95% of the tools you need for the cleaning. It's available in all our Edge and Edge 8 systems. I'm going to show you the Edge 8 system now. And also it minimizes the decrease transfer between the connectors and the modules, because there is no decrease. So Edge 8. So remember when I told you that when we migrate from a 12 fiber system into a QS and try to connect to a QSFP, which is using 8 fiber system, Corning in 2017 decided to come up with a new solution called the Adject. The Adject would change everything to be base 8 and not base 12. So the trunks now are multiples of 8. You can buy them like 8, 16, 24, 32, and so on. So it's all multiples of 8. And then we also made smaller modules, MTP to LC modules, which is also 8 fibers or 4 ports. And then when we do the migration, we switch to a 4-port MTP and an MTP to MTP jumper, which is 8 fiber. So everything is in 8. So you don't lose the 4 fibers, which is in the middle. And at the same time, you don't need conversion modules, which increases your loss. Also, it has high density. We maintain, the density of the same 144 in 1U, 288 in 2U, and 576 in 4U. And also, we can manage more and more cables inside our panels. So this is like the components. Trunks, which starts from 8 fibers, and it can go all the way to 288 fibers. This is the MTP to LC modules of 8 fibers. We also have the MTP to MTP module. We have the LC to LC jumper and the MTP to MTP jumper or patch cord. Then we have our famous breakout cables, which we can connect to a QSFP, 40 gigabit, and break it into 4 10Gs. And also, Corning developed a breakout module, which do the same exact function, but it allows you or gives you more flexibility. So this module can connect to a QSFP sitting in a cabinet, and it can go all the way to where the servers are, and then it can connect to different servers. Not unlike this MTP to LC breakout cable, it has to connect to the exact same server. It cannot connect to 2 different servers. This one allows you to connect to multiple devices in your data centers. And again, we have the 1U 144 fibers, as I mentioned before, all the way to the 576 4U fiber panels. They are backward compatible to each other. So you see, for example, if you have an existing Edge 12, base 12 system, you can also implement an Edge 8 system inside your same patch panel. All what you need to do is just to change the trays. So a tray of Edge fits 4 cassettes. Meanwhile, a tray of Edge 8 will fit 6 Edge 8 cassettes, which is exactly the same density. Everything we produce, 100% is produced in Corning factories. We have 3 main factories globally for the data center solutions. Reynosa in Mexico, which covers the North America region and Americas region. In Europe, Middle East, and Africa, we use our factory in Stryków in Poland, which supplies this region with all data center solutions. And for the Far East or the APAC region, we use our Shanghai, China factory, which supplies data center solutions for this region. So this is how our Stryków plant in Poland looks like. We had the SPW or Stryków West was open since 2006. Stryków East was open 2 years ago. So we kind of like doubled our manufacturing capacity 2 years ago to be able to meet your timelines. As you can see, the size of the factories compared to the like small tiny cars. These are like almost 8 football size fields. And this is actually where our products are produced. And everything we do there, from connectivity, pigtails, patch cords, pre-terminated solution, the edge hardware, modules, cassettes, breakouts, everything comes from the same place. And this is the biggest factory which produces structural cabling in general in the entire continent of Europe. So this is like the last, I would like to, if you have any questions, please let me know and I will clarify more the presentation.
Thank you, Mahmoud. I will stop the recording now.